right, back to graphing. There are many types of graphs. If you've ever played around with Excel, you can see, there's a ton of different choices you could come up with, but we are going to stick with the three simple ones: a bar graph, a pie chart, and a line graph. You guys fill that in. Okay. So bar, pie, line. Starting with bar. I think a few of these things are blank for you, or maybe one of them is. What's so good about a bar graph? Well, it's pretty easy to tell the difference between a big bar and a little bar. Okay, it is easy to compare data that way. So here is some random bar graph. We got temperature in degrees Celsius on the bottom, and then it says number of rooms. So maybe these are number of rooms in the school currently. And it'll tell you, well, let me ask you a random question. Make sure we can read some graphs. So where's Jordan? Okay, Jordan. How many rooms are at 19 degrees Celsius? 2. Okay, 19. Check it. 2 rooms in the school are at 19 degrees Celsius.
Is that cold or is that hot?
Room temperature is actually more like 21, 22, which that's around 70. Yeah.
So 16.
So it's a little bit cooler, yeah. So somebody's pretty cold. All right, Kara. The most number of rooms in this school are at what 2 temperatures? Yeah. I got 5 rooms each at 21 or 22 degrees Celsius. All right, so this is a lovely bar graph. We can compare data. We can tell that more rooms are at 21 or 22 versus, say, the one at 16. But it's still not a perfect graph. There's something missing. What would every teacher like to see on this graph? A title. A descriptive title, like temperature at rooms in Easley High School. All right, now our pie chart. Pie chart, you want to associate the word percentages with. Pie chart would not apply to every type of data, but if you had data that was part of a whole, and we could do that for temperatures at the room, or temperatures of the room in the high school, if we knew how many total rooms we had, we could make a pie chart out of that as well. Okay, so this graph, we've got gas, 50%, steam, 25%. When I ask you to do a pie chart, I'm not gonna get out a protractor and make sure you've got your pie pieces exactly right as the percentage should be, but try to use your common sense, all right? We know 50 is half of the pie, and then for smaller pieces, just don't have the smallest piece, like the 5% piece, be bigger than the 10% piece. That's what I'd kind of be looking for there. So we've got electric, coal, other, steam. So these are obviously some power sources of something. And I could ask, let's see, Blake, what type of power is used 25% of the time? Steam. All right, easy. Pie charts. Line graphs. Last one. Line graphs are very commonly used with something changing over time. Time is often on the x-axis. Doesn't mean it always is. So we could have temperature versus time. Typically, line graphs are used when both your sets of data are numbers, pressure and volume, velocity and time, things that I've measured that are actual numbers. And line graphs, of course, are nice because they show trends in data. You can pretty easily tell if the line's going up or the line's going down, or maybe the line's just staying constant. And so that helps us make predictions as to what the data would do like in the future. This is a pretty interesting graph, one we'll talk about later in class, because it actually does look like this. This is the temperature of, I don't know, imagine you had like a thermometer stuck in a chunk of ice and you set it on the stove in a pot. Well, if you set it on the stove and you turn it up, of course the temperature is going to go up, 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 up. But interestingly, it flattens out from time to time. Why does it stop increasing for these instances in time? Well, because pretty much what it says is happening here. When you have a phase change, you actually need a little extra energy to sort of break apart the bonds that keep water molecules in the ice format and turn them into the liquid format. So when you have melting, ice to liquid, it takes a little bit of time for the temperature to start going up again because we need that energy for other things. Same here when it's going from liquid to gas. And of course, missing a title again. All right, here's another graph. This one's distance over time. So you can imagine somebody's like just running around the track or walking around the track, moving around the track. We got the red person, the blue person.
I'm the red person.
All right, so Trevor, look at the red person. Can you see, where does the red person make it after 30 minutes? Good, 2,400 meters. After 30 minutes, that's how far the red person has gone. Janu, how about the blue person after 30 minutes? 1,200 meters. Okay. So, red person is clearly faster, gone more distance in the same amount of time, must be going faster. I want to know a little bit more about this blue person. Where's Hannah? Hannah, what is happening with the blue person between 10 and 20 minutes? Very good, he's stopped. Ever see a flat part on a distance graph? Well, my distance is staying the same. I've gone 400 meters, I'm still at 400 meters, I'm still at 400 meters. So obviously that person is still. So the slower blue person needed a break.
10-minute break.
10-minute break. Walking around the track is tough. All right, rules for making your own line graph. So we know a little bit about how to read graphs. Now we want to make some of our own. There are rules for where the variables go. Whether it is a line graph or a bar graph, this would be true. But you got to determine, what's what, the independent and dependent variables. So hopefully we remember this from back when we were talking about scientific method. So when we talked about the scientific method and creating a good experiment, we always had to have an independent, dependent, and a bunch of control variables. Independent variable was the thing that the experimenter changes purpose. It's kind of what you were setting up. So in my example of measuring a child's height each year, that's something I could easily graph. Amanda, what is the independent variable there? What is it that you are changing on purpose, sort of, that you are deciding to do?
Is it the height that it is? No.
Do you, the experimenter, affect the kid's height? No.
How much it eats? How much?
Well, yeah, you would want to feed the child. That is true. But what you're checking for is height. I mean, you have really no control over the height. Well, I mean, assuming you're not feeding your kid or feeding your kid, but yeah.
Isn't time always the independent variable in any
all right, for example, let's say you want to do an experiment where you had, I don't know, a couple different types of bread, and you want to see which one got moldy first. The independent variable would be the types of bread. In that case, the dependent would be the time. How long did it take? I didn't really control how long it took. But very often we are setting the time interval. We're going to check something every day. We're going to check something every minute. In this case, every year. I, as the experimenter, have decided that I'm going to check this child's height every year. So the independent is the time, and what maybe depends on the time and probably does depend on the time, well, that's the height. So once I figured out what's the independent, what's the dependent, now I've got to put them on my x and y axis appropriately. And maybe often your margin. Yay, yes. Or not. I need more room. I'm just going to color. You guys keep writing. Don't worry about me.
Oh, you want to draw?
Yeah, I want you to get your yellow pencil. All right, sounds like you guys have heard of dry mix before. Yeah. This is just a helpful trick to remind you what variable goes where. So in our last example, we're going to graph the child's height every year. Well, what goes where? Well, we said the independent variable was time, which it often is, not always, but often. So that's got to go on the x-axis. So the I in mix stands for independent. The x obviously stands for x-axis. What's the m?
Manipulated.
Good. Manipulated, just another way of saying independent variable. I would write that in your margin, but I mean, sounds like some of you already know it.
Yeah.
And then what's the dry part? The y is y-axis. Good. R would be responding. Hopefully yours is a little less messy than mine, but and there you go. So hopefully that will help you remember where they go. Of course, when we're making a graph, we want to label the axes, include the unit, usually include the unit in parentheses, and determine an appropriate scale. Try to always make your graphs as big as possible so it fits on a page, but as big as possible. Itty-bitty graphs, it's kind of hard to tell what's going on there. Make a descriptive title, plot your points, and maybe, if appropriate, draw a line of best fit. That's something we'll get to a little more in the physics part of the year. And maybe you've learned that in math already. All right. So here is a graph. Distance, time. There are two things wrong with it. Leah. Shh. Sorry, I'm going to call on Leah. Tell me something that is wrong with this graph. There's no title. It's a distance versus time graph. Now the other one you might have to look a little more carefully to find. Wait for it. Kennedy.
Oh, they're different numbers. They're going up by different.
You are not Kennedy. You missed your turn. All right, your scale is incorrect. These were likely the person's data points. Although it's unlikely your independent variable would not be at set intervals. You would definitely do that at set intervals. But and if this spacing is 2, then from 2 to 3 can't be the same spacing. That is a poor scale. Go up by 2s, go up by 5s, but 2, 3, 7, 10, 11 all spaced out the same. That is poor. All right, here's another graph, volume versus pressure, which actually doesn't even make sense the way this is graphed anyway, because as the pressure of something goes up, like imagine sitting on a basketball, you're increasing the pressure inside that basketball. Would it get bigger? No. So that graph's backwards. But anyway, just looking at what would be missing or incorrect about it. Will, can you tell me something? Yeah, I don't even have numbers over here.
No numbers.
So that's a problem. And Shandini, what's the other one?
There's no measuring unit for volume.
Yeah, there's no unit. What am I measuring volume in? Meters cubed, centimeters cubed, milliliters, liters? What am I measuring?
You know, you know.
I don't even know. And it's a backwards graph. It's just so wrong. But it does have a title.